goes down. So we were interested to see if we could tell if there's differences between the top cross and how the top cross reacted compared to the wild stand. And the way that we can do this is to summarize the vertical distribution of the foliage using a Weibull probability density curve. And I'll get into that a little bit later. This is just a brief overview of the method. So we do our data acquisition, followed by automatic segmentation, and then we did some manual segmentation from the automatic segmentation before we could produce our Weibull curves. Our field site was on the Sunshine Coast in British Columbia, as you can see here. And just in that photo, you can kind of see the immense care that was taken to make this really grid-like pattern. And you can see that in the slide that shows that for the acquisition. So we flew the data in June 2018 with the help of Arthur Lucier from the University of Tasmania. And one thing I just want to point out is that we got a final point density of about 650 points per square meter, which at the time we thought was very, very high density. Maybe not so much at this conference. But this is what the data looks like. So this is the entire site, and you can really see those trees in the grading fashion, and then that's what the cross-section looks like. So it is still pretty dense LiDAR. So after we had done the data acquisition and we tidied up the point clouds, we used an automatic segmentation using the Lee algorithm, which we implemented in LiDAR, the LiDAR package in R. And it actually performed pretty well at the 4-meter spacing. At the more dense spacings, we had to go in and automatically remove some of the overlapping branches from other trees, but it did a pretty good job. So once we had segmented these trees, we could finally create these curves for every tree to kind of characterize the vertical foliage profile. We chose the Weibull probability density function just because it summarizes the vertical distribution using two very simple parameters: the scale and the shape parameter. So over here you can see the shape, the scale parameter rather. So as you increase the scale parameter, it has an effect on pulling the curve upwards, so where the position of the curve. Whereas the shape parameter has an impact on the breadth of the curve. So as you increase the shape parameter, the breadth actually decreases and it pulls the curve out. So we did this for 30 trees of every genetic level and spacing. And then we could go on and do a two-way Anova because we had we had the genetic level factor, and then we also had the spacing factor that we had to take into account. We could then do a post-hoc test to compare the means of these and to see what is significant. So here you can just see, this is an example of top cross trees and wild stand trees and how different the curves actually look. And so for our results, we found that the interaction factor was significant, and so we had to produce these interaction plots, which you can look at both the genetic level here, as well as the spacing, which is the different colors. And we did see that in both the scale parameter and the shape parameter, there were differences at the more dense spacing for both. Unfortunately, there were no differences at 2.9 meters or 4 meters, but here you can kind of see what the differences between the wild stand and the top cross look like. In addition, we found that there was a greater variation among the top cross trees compared to the wild stand trees, and this could indicate phenotypic plasticity, which I argue is a positive trait because moving forward, when we go to plant these trees all over the province, we're not going to be able to plant these at necessarily an optimal spacing. So we want trees that can perform well in a variety of spacings that you know will be okay. So really, what we found out was that, yes, we can produce and characterize these trees pretty well using this data, and it provides a new opportunity to a new framework that we can look at phenotyping individual trees and do a better job of selecting for trees, as opposed to having these long breeding trials, we can now go out and potentially look for these phenotypic extremes and select trees based on that, because we know that they are going to produce trees that have a great quality. This also kind of helps us to keep that diverse seed bank where we don't just limit ourselves to a small number of trees. And it can also be kind of put into other end goals. So obviously as we move forward and we're interested in drought resistance and things like that, we can start integrating this. We can also repeatedly collect this information. So it's really nice that we can go away and take these measurements every few years and see, are the characteristics that describe these top cross trees the best trees? Do they change with time, or is it something that is stagnant? And yeah, we can kind of investigate, we can look at the temporal aspect of the data set as well. So moving forward and ongoing work, we're interested in producing, this was just one example of a characterization. We've done quite a bit of work on external crown characterization. So now we're going to start looking at internal crown metrics. Are the top cross trees somehow different? Do they have maybe the symmetry is different of the tree, as well as looking at intensity metrics from our LiDAR data. We also have a couple of other data sets. We have some spectral data that we flew at the same time, the same data acquisition. So that's some near infrared data that we're also going to look into to see if there's spectral differences between the trees. And so yeah, I'd just like to say thank you to who funded this project. And that's that.